¿Por qué? It's been... Vale. Sí, bueno, sí, antes se la probé y parecía que sí, que ya funciona. Sí, sí, sí. Sí, que ALMA fue hackeado. Y estuvieron un mes y medio parado completamente. Sí, 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 sí. Sí, sí, sí. Afortunadamente fue una entrada y no entraron, o sea, no les dio tiempo de acceder muchos datos, con lo cual pudieron cerrar todo. Sí, sí, sí. Es un problema porque sí, un mes y medio sin observaciones y eso se pierde. Sí, sí. Para este ciclo, es decir, que muchas propuestas que en condiciones normales se hubiesen observado, no se observarán. Sí, sí, sí. No.
Hola, ¿qué tal? Buenos días a todos. Muchas gracias a los que están aquí en el auditorio y a los que están conectados en Zoom. Hoy tenemos un coloquio extraordinario a cargo del doctor Josep Miquel Girart de Barcelona, quien es invitado del doctor Salvador Curiel aquí en el Instituto de Astronomía en CU. Entonces, Salvador nos va a dar una pequeña semblanza del invitado y después comenzamos ya con el coloquio.
Ok. Bueno, José Miguel, de hecho, es viejo amigo no solo de nosotros, los que hacemos formación estelar en el instituto, sino del instituto mismo. Él venía con frecuencia al instituto, hace rato que no venía, y con lo de la pandemia, pues menos. Pero él viene de vez en cuando y nos da pláticas, nos ha dado unas pláticas que creo que no se han repetido, como polarización en flujos moleculares. Esa plática la tengo en mi cabeza todo el tiempo, en fin. A José Miguel lo conozco desde hace ya 30 años, algo así. Nos conocimos cuando yo estaba de postdoc en el CFA, en el Centro para Astrofísica, en Boston, Massachusetts, y José Miguel llegó a hacer su doctorado asociado a Paul Ho y Robert Staleya, y yo estaba haciendo mi postdoctorado con Paul Ho. Entonces ahí nos conocimos en el grupo de Paul Ho. Y inmediatamente empezamos a interactuar y empezamos a colaborar. Y esa colaboración se ha mantenido durante todo este año, todo este tiempo. Y eso fue en 1997, no es cierto, 93.
93.
Entonces ya tiene 30 años. En fin, después de terminar su doctorado en el CFA, José Miguel se fue a la Universidad de Illinois en 1997, para hacer una estancia postdoctoral. Ahí inició algo que yo creo que modificó su trayectoria profesional. Empezó a trabajar con polarimetría en radio, y ahora es algo que es lo que hace mucho. Posteriormente se fue a Barcelona a hacer un postdoc en la Universidad de Barcelona en 2001, y luego en 2004 consiguió una plaza de Ramón y Cajal, que es del Ministerio de Ciencia de España. Esa ya es una tenure track, es como ya un trabajo, pero no es permanente, todavía es temporal. En 2007 ya obtuvo la plaza permanente como científico titular, y desde entonces está trabajando en el Instituto de Ciencias Espaciales, también en Barcelona. Entonces, José Miguel es un experto en formación estelar, alta y baja masa, que creo que se ha desviado más a alta masa desde hace un buen rato. Y es considerado un experto mundial en polarización y campos magnéticos en regiones de formación estelar. y su plática de hoy gira alrededor de eso. Formación estelar y polarización en regiones de formación estelar. Adelante.
Muchas gracias, Salvador. La plática la haré en inglés, pero si quieres hacer preguntas luego en español, no tengo ningún problema. Okay. So thank you very much to Salvador, to the Institute, for allowing me to give me this talk about the update of ALMA observations. ALMA, you know, it's a millimeter array. It's the most powerful millimeter array we have. It's in Chile, in the northern in Atacama Desert. It basically covers all the millimeter and submillimeter spectrum that we can observe from the Earth. Okay, and it's very powerful. So okay, let me see. Okay, so this is going to be my the outline of the talk. So I'm going to divide the talk in 3 parts. First, I give you a present update of which are the polarization capabilities with ALMA, just in case some of you are interested of using ALMA and specifically using polarization observations. You can contact me, of course, and just to let you know which is the status. And then just a very brief introduction of what does polarization trace on millimeter wavelengths, to know which kind of science we can do, and then results with ALMA. First, I will try to do kind of 2 very important results on a very general perspective, and then specific results on specific sorters. Okay, so let me start first with ALMA. ALMA is an aperture synthesis telescope. It has like usually 40, 45 antennas observing simultaneously. They correlate the signal. Each antenna has can measure linearly polarized emission, the 2 of them, and they correlate that in the correlator. So you can measure the Stokes parameters, Stokes I, Q, and U and V. And the Stokes I total intensity, the Stokes Q and U are the Stokes parameters that allows us to get information of the linear polarization, and Stokes V, it gives you the circular polarization. Okay, so if you ask for with ALMA, you can request dual polarization, so you only get the Stokes I, or you can request the full polarization capabilities. But these are limited, so it's good that you know which kind of signs and frequencies you can use. So let me start with the linear polarization capabilities. So ALMA covers now, starting this cycle, is going to cover from 7 millimeters, that's band 1, all the way to almost terahertz wavelengths. Okay, and this is a plot of the transmission of the atmosphere. So in every patch where you can observe from Atacama, there is a receiver that allows you to tune the receivers at that frequency. Okay, however, within polarization, you can only use the lower frequencies, so covering basically from 3 millimeter all the way to 800 micrometers. Okay, so you cannot use polarization in the high frequency band. So that's something to keep in mind. In addition, there is some constraints. Okay, so the accuracy of the linear polarization is of the order of 0.1%, which is excellent. So this is not an issue. Okay, however, because of the way you solve for polarization calibration, you can only use the 1/3 of the primary beam. Okay, of the field of view. Okay, if you want to try to explore and detect linear polarization at larger scales, a larger field of view, then you have to do mosaicing. And in present, you can only do mosaicing in continuum, and probably in the next cycle, or 2 cycles from now, you will be able also to do mosaicing for spectral lines. So let me just skip that. That's too technical. So for circular polarization, the circular polarization, that's not well implemented in the sense that they have not been able to solve all the technical issues in the process of calibrating any instrumental response. So right now is quite limited. You can still do a circular polarization between 3 millimeter and 100 microns in all the bands, band 3, 4, 5, 6, and 7. However, you are limited to a strong signal in circular polarization. So in order to propose data, you have to show that your signal is above 2% or higher. If you have a weak signal, you shouldn't use that because the instrumental polarization may be an issue. Okay, and in addition, because of the beam squint, you are limited to the 1/10 of the primary beam. So you can only do circular polarization observations if you're circularly if you know that the Stokes V is going to be strong and compact within the center of your image, and you cannot do mosaicing. Okay, so this is quite limited, and this is really bad news for the people that wants to use Zeeman observations. I will show you about Zeeman observations. Okay, so which are the traces? Which are the traces that to study star formation with ALMA? So ALMA is a millimeter telescope, as I said before, all the way from all the 7 millimeter to about 300 micrometers. Okay, so for the galactic studies, ALMA is an excellent instrument to study star formation at the scales of the order of from these scales. We are talking about few AUs. If you have a nearby disk, all the way to few thousands or 10,000s of AU. If you are observing molecular clouds out in the outer galaxy. Okay, and what it proves. It usually proves the densest parts of the molecular clouds, okay, dense, which typically are relatively cold. We are talking about molecular gas and dust, which are usually at temperatures of few tens of kelvins. In some cases, you can go up to few hundred kelvins, but these are the ranges of temperature that you are sensitive to, and regions with that are very dense of the order of 10 to the 4 all the way to 10 to the 8 particles per cubic centimeter. Okay, and this allows us to study which are the physical process during the star formation from both low mass, high mass, and even planet formation. Okay, so what about magnetic fields? In order to be able to observe magnetic fields, we want to the best way to do it is to use polarization. Okay, polarization is the best tracers to study magnetic fields. And why do we care about magnetic fields? We care about magnetic fields because in the molecular clouds, even this molecular, the content, you have about 10 to minus 6 you have an ionization fraction of 10 to minus 6. And you may think, okay, 10 to minus 6 or lower, these are really small values, but are high enough, such as the gas, molecular gas is coupled with the magnetic field through collision with ions, which is basically electrons and molecular ions like HCO plus, H2 plus, etc. Okay, so how we can use now polarization? So there are several ways. So let's start with molecular lines. Okay, they are polarized. Why they are polarized? Because we have a rotational level, which are usually the typical levels you detect in millimeter wavelengths. Okay, under the influence of a magnetic field, the rotational lines split into submagnetic levels. Okay, and this rises to that the emission is polarized. Can be linearly polarized or can be circularly polarized. Okay, so for example, just as an example, if you have observing a region where the magnetic field is along the line of sight, the linear polarization from the P transition will be 0, and you have only circular polarization, where you have the two states, +1 and -1, two magnetic levels, which are circularly polarized. One is left-handed and the other is right-handed. And they emit with a slightly different frequency. So you have the spectral resolution. In principle, you should be able to see the two left and right-handed splitted. However, this splitting usually is very small. So you can resolve that. The line width is much larger. But because you have left and right-handed, you do left minus right, you have the circular polarization, and that will be the derivative of the spectral profile. So you can measure the circular polarization, and that gives you an idea of the magnetic field strength. Okay, that's proportional to the magnetic field strength on the line of sight. So that's by observing the circular polarization, that's the best way, that's the only way, in fact, to measure the absolute value of the magnetic field, always the component of the line of sight. Okay, there is another mechanism, which is the linear polarization. If there is any mechanism where the collisions, the population of the submagnetic levels is not equal, that will arise linear polarization. So that's another way to measure the magnetic field. That doesn't give you information of the magnetic field strength, but it's going to give you information of the magnetic field projected in the plane of the sky. Okay. So that's one way. Okay. So you have the two effects: Zeeman effect and the linear polarization that arises when you have unequal populations of the submagnetic levels, which is called the Woolrich-Klafis effect. Okay. As I said before, Zeeman effect is the only way to measure a strength of magnetic field. However, with the limitations of ALMA in circular polarization, I think this is not very, it's basically unfeasible. I mean, there are some groups that have tried to do Zeeman observations, but it's really, really hard. On the other hand, measuring the linear polarization is probably more feasible, okay? So that's two possibilities to do, to measure magnetic fields. And there is the third one, which is the most used one, because that's where you have usually signal that is strong enough to detect it with ALMA. ALMA is very sensitive for the continuum emission. So this mechanism is basically detecting the dust, the linear polarization of the dust emission. Okay, and how that arises? This arises because you have spherical grains, and they have kind of paramagnetic inclusions. The grains are going to be aligned with the magnetic field. Okay, so the emission is going to be perpendicular to the magnetic field, and we're going to enter which is the mechanism to align the grains, because this should be just a full talk for that, but that's the result. You have linear dust polarization, where the emission, the polarized signal, is going to be perpendicular to magnetic field, the projection on the plane of the sky. So this is another way to do it, and this is the most used way to study magnetic fields in star-forming regions. Okay. In addition, I mean, that's for star-forming regions, but with ALMA, one of the first things we already knew that ALMA is going to be a major change in science was planet and disk formation. Okay, with the sensitivity and angular resolution with ALMA, you can really explore very well which is the physical and chemical properties of the disks that are forming planets. Now we are, before it was a protoplanetary disk, now we call it a planet forming disk, because we already know, we already see that there are indications that in this disk around young stars, there are already planets being formed. Okay, so of course the idea of using polarization to study the properties of the magnetic fields in the formation and evolution of the disk and the relation with planet formation, that was of the main topics initially we have. However, that happened. Bam. That's not possible. And I was going to explain you why this is not possible. But you can see it's a big stone. So this is what is happening in planet forming disk. In planet forming disk, this is a well-known thing, is because of the densities, the physical condition, grain growth is a major thing. So dust particles growth all the way up to almost millimeter size scales. And when you have that, what happens, because you're in the millimeter regime and you have kind of close to millimeter size particles, then the scattering opacity becomes larger than the absorption scattering, the absorption opacity. And what that means, that the polarization in this case will be dominated by self-scattering. Okay, so that's what we see. And here is an example, two cases in the near infrared, because on this surface you have small particles. When you observe in the infrared, you see scattered light on the surface of the disk. When you go to millimeter wave, you basically are very sensitive to the dust particles in the midplane, and because they are large, you are going to detect there the self-scattering. Okay, but the picture is even much more complex. So first, self-scattering is going to be dominant, probably. Okay, but in addition, there are other mechanisms that could contribute to the dust polarization, which makes the situation really a mess, or at least very complex. So you have also some models that predict that you have spherical large grains, you may have alignment with radiation, what is called the Girart. Another mechanism is you have a drift between the gas and the dust particles. This will induce polarization, because the grains will be aligned with the velocity gradient. Okay, so this is another possibility of polarization. There is another one, fifth mechanism. This is the polarization reversal of self-scattering, which basically will be the opposite in direction. But this is expected to be very small. But in any case, can happen too. And then there is another mechanism that we found recently, that because you have large particles, when you are using wavelengths that are slightly smaller or similar to the particle size, what happens, you are in the mid regime. And then if you have large grains that are sphericals and they are aligned with the magnetic field, which is not clear that this happens, then the polarization is going to be parallel to the magnetic field, which is the opposite that we were explaining before. So you see all these possible ways to polarize the dust emission. So that makes the studies of dust polarization very interesting, but very complex. And there's still many people I mean, the expertise on that, they don't agree which is the main mechanism. But when you go just from the observational point of view, and you go to the disk scales, and you see what is the polarization pattern, here are several examples. This is a massive disk we have studied, which is the HH8081 jet. This is the disk around this jet. And all these are planet-forming disk around low-mass young stars. This is around a high-mass star, around 20 solar mass already. In all these cases, you can see a pattern that repeats from disk to disk, and where the polarization is basically parallel to the minor axis. This is telling you this is the spectral polarization pattern by self-scattering. So this is the dominant. That's something that we already know. But the problem is when you go to different frequencies for the same source, the polarization pattern changes completely. And I'm not going to enter into that. And this is why nowadays we still don't know what's going on. Okay. But the bottom line here is at this scale, so far using dust polarization is not a good tracer of magnetic fields, which is the thing I'm interested in. Self-scattering can be used to understand grain growth. That's very good, but not to understand the role of magnetic fields in the dust in the disk evolution. Okay, so now let's leave the planet-forming disk. Let's move to star-forming regions at the core scales. I'm talking about a few thousand AUs all the way down to a few hundred AUs. Okay, so and this is the typical. This is like the scheme of how a star formation takes place in a very simplistic way. You have a core that is gravitationally unstable and will start to collapse. And because you have some initial angular momentum, you are going to create like a flattened structure, and it's going to become a planet-forming disk. Okay, and because at some point you need to remove part of the angular momentum, you see observationally these highly collimated jets, both in continuum, in free emission, or in molecular content, like using CO. And as the core evolves, the material starts accreting toward the disk, from the disk toward the star. At the end, you're going to have a star surrounded by the planet-forming disks. And at the end, after several million years, you may have a planetary system. Okay. However, in this picture, there is one physical mechanism that is not showing here, which is magnetic fields. Okay, so with our group, what we're trying to figure out is which is the role of magnetic fields in the process of star formation, because that can be important, for example, by removing angular momentum. We know magnetic braking is probably happening at these scales, and it allows the accretion to go to the disk and from the disk to the star. And the magnetic braking, the magnetic fields are probably responsible to launch these highly collimated and high speed supersonic speed jets that can travel several hundred kilometers per second. Okay, also magnetic fields are very important in the way the disks form, because if magnetic fields are too strong, it may suppress the formation of disks. You will have only a very, very tiny disk. And in addition, magnetic fields can also suppress fragmentation. Okay, this is maybe important to form massive stars. Okay, and okay, so there are several implications to better in the sense of understanding which is the role of magnetic fields. For massive stars, of course, the picture is a bit more difficult to understand, just because they are usually farther, and because the young star enters to the main sequence when they are still in the accreting phase. Okay, so it makes things more complex. There is the possibility that the way high mass star forms is the same way that low mass, but on a larger scale, or through other like competitive accretion method. So now I'm going to talk about magnetic fields. When before ALMA, I was working with BIMA, then with the SMA, trying to detect the dust polarization. And I remember one of the main criticisms, especially from the theoretical point of view, it was the first, are the dust grains aligned at the core scales, which is something that is not so trivial to answer. Why is that? Because the grains we already know that at the core scale there is also grain growth. At some point, the grains may not be aligned with the magnetic field, right? If they are too big. Okay. And the other thing, the theoretical people was complaining about us, and we couldn't answer, is the magnetic field well coupled with the gas? Because at these densities, if you expect that the ionization fraction decreases with density, at some point,
the magnetic fields will decouple with the gas, okay? And this is very important questions that we were not able to answer. But now with ALMA, we're going to show you that we already answered this. So first, with ALMA, we already observed many regions, nearby regions, low mass star-forming regions in Taurus, in Perseus, in Orion, in Serpents. So what we did with a student, Valentin Legoulet, is to collect all the data available at that time. And because we have a very good image fidelity, we have a lot of polarization detection for each field, we have a significant statistics that we can use to understand the dust properties, the polarization properties of the dust emission at the millimeter wavelength of this star-forming cores. And we're basically used as a reference Planck work. Planck has done a lot of work on the dust properties, and what we measure, in this case, what we use as a proxy to understand the dust grains alignment with magnetic fields is to use basically two quantities. The dispersion, which is measure the dispersion for each position in the sky of the around that pixel. So you go just around 1 beam away and you see how much is the dispersion, and also the polarization fraction at this position, okay? And we do the statistic, and this is what Planck did. And this is statistics of Planck, where you see here polarization fraction in the x-axis, and here you have the dispersion. And you see this kind of anti-correlation. So for when you go to high dispersion, you usually tend to have low polarization fraction and the reverse, okay? And in fact, if you fit like a power law, this goes to -1, more or less, okay? The anti-correlation between polarization fraction and dispersion. However, if we want to do the same analysis with ALMA, we have to think about that ALMA filters out the extended emission. We are not sensitive to the large scales, okay? So in order to proper relate or compare the ALMA results with the Planck, the first thing you have to do is how ALMA will see Planck data. And for that, what we did is take all the cores observed with Planck, and we move it far away, so the core size is more or less similar to the field of view of ALMA, and then filter out the emission. And what happens is this: you start to do again the same relation of the dispersion with polarization fraction. You see the results. You see is there is a bias toward large dispersions and polarization fraction. Okay, so the power law becomes more flattened. Okay, and this is just an effect of filtering effect. Okay, so this is something to take into account, because if you want to compare with data with Planck, we have to compare this plot and not this one. Okay, so how ALMA shows this kind of relation. So here it is. Okay, so this is the relation of the dispersion with polarization fraction. Okay, for all the data we observe for low mass star-forming cores. So what you see is this anti-correlation, but it's not the anti-correlation you see with the Planck data when you filter out the Planck data with ALMA. Okay, it's something a bit more steeper, and that's related with the properties of the turbulence in the star-forming cores, which is already telling you that it's probably slightly different of the turbulence in the interstellar medium when you have these small dust particles picking up with Planck. Okay, so this is already telling us that the turbulence properties are different in the star-forming cores than at the cloud scale, molecular cloud scales. Okay, the other thing that is very important is if you multiply the dispersion with polarization fraction, okay, this is a proxy of the grain alignment efficiency. Okay, that's already was shown with ALMA, with Planck. Okay, I don't know the details why this is the case, but this is a proxy of the grain alignment efficiency. So Planck used that to see the properties of the alignment efficiency at different column densities, okay, of molecular clouds. So we did the same. So we computed this parameter, dispersion times polarization fraction, and we did it as a function of the column density. Okay, this is normalized column density to respect to the peak. Okay, to have all the data in the same, because we have cores that are a bit more massive than the other ones. Okay, and the gray, and there is a lot of dispersion, but the gray line here are the median points, okay? And you can see that this there is a trend to slightly decrease this value, dispersion times polarization fraction with ethnicity, but it's a very, very smooth decrease. It's not a large decrease. So that tells us that the polarization efficiency decreases a little bit, but not too much. Okay, so grains are well aligned within the star-forming cores, which is very important because we are answering already to the people that was a bit skeptical that dust polarization could be used to study magnetic fields. Okay, in addition, I think that's even more important. When for that, we use some MHD simulations of star formation in non-ideal MHD from, I think, was from Patrick General group, and what we did is to create synthetic maps of dust polarization and do the same mechanism by using two possibilities: perfect alignment, which is here PA, or using the most sophisticated theory of grain alignment, which is the RATS, relative. I always is relative alignment torques theory by Alex Lazarian. So we use the two cases, and we also used using the simulations. We computed these parameters as a function of column density for two cases: for filter emission with ALMA, taking into account the ALMA response, or just without any filtering. Okay, so what we found when you filter with ALMA results, this value becomes a bit higher. But what we found is the RATS theory, which is the most sophisticated one in order to understand grain alignment, fails to reproduce the ALMA data. So here what we are saying is that the grain alignment at the core scales is even much higher than expected by the theory. Okay. We also divided the cores between high luminosity and low luminosity, and when we do that, we already see a trend that the low luminosity cores usually has a less efficient, less alignment efficiency than the higher luminosity, which is what you expect from RATS. But RATS cannot provide the quantitative values of this parameter as a function of column density. So that means the grain alignment theory is not well understood yet. But dust grains are well aligned with magnetic fields, which is the main answer we wanted to do, because then we are confident that we can use that in order to study magnetic fields during this at the core scales. Okay. The other thing about the ionization fraction. Okay, that's the other thing that the theory was skeptical about the core scales. Maybe, yes, you see dust polarization, traces magnetic fields, but this is not well coupled with the gas, so it doesn't matter. Magnetic fields are not relevant to the magnetic field. So what we did is with ALMA, we use chemistry to try to answer this. So we use some spectral lines, observations. We selected a target, B335, which is a double quote typical low mass star forming region, which is not so typical. And this is isolated, which is good. So you are not affected by feedback from other star forming regions. So the physics is just because of the gravitational collapse to form the star. It's one solar mass, typical of low mass, two solar volumetric luminosities, distance relatively nearby. Okay, and the interesting thing of this source is it has a very tiny disk, less than 10 AU, which is a factor of few smaller than in other class 0 protostars. Class 0 are the youngest protostars. Okay. In addition, this region has been observed by many groups, a lot of them. And what they found at the core scales or the outer core scales, you see some kind of rotation. But when you go to the inner part of the core, in the inner part of the envelope, the rotation disappears. You cannot measure rotation. So the gas apparently is probably only accreting toward the center without angular momentum. Okay, so this was we thought that it was a very interesting target to study magnetic field, because this already give you some hints that magnetic fields is playing a role in by removing angular momentum. And from dust polarization, we already saw that there is a very well organized magnetic field because of the filtering effect. You see this kind of shape, but it's compatible with a typical hourglass. And we also compared that with the non-ideal MHD models from the general group, and we could we could constrain the magnetic field. Is a supercritical core where magnetic field is relevant in the sense that it's strong enough to remove the angular momentum. Okay, let me skip this part about the kinematics because this is also very interesting, but I don't have time. Okay, but the interesting thing here is we were able, using molecules like DCO+, HCO+, and isotope homologs of CO. In all cases, we use spectral lines that we know that are optically thin to derive or constrain the ionization fraction. And the ionization fraction here is the panel on the right here. This is the scale, okay, 10 to minus 6. And you can see all the values are few times 10 to minus 6. This is a lot, okay? You expect that the score scales, that will be 1 or 2 orders of magnitude lower if the ionization is produced by external cosmic rays, okay? In addition, you see the color scale, red is higher than blue, and you see a gradient of increasing ionization fraction toward the center. Okay, this is not expected. This is not what you will expect from external cosmic ray. External cosmic ray, you will see the opposite. Because of the larger column densities, you will see a decrease of the ionization fraction toward the center, and we see the opposite. When we convert that into ionization fraction, we still see that, and the values are really high. 10 to minus 15, 10 to minus 14, and this is really surprising. If during the full protostellar evolution, the ionization fraction, the ionization rate is so high, CO will be completely destroyed. So this is telling already us something that this has to be kind of a temporary effect, maybe some flares that is ionizing the core, okay, like a accretion burst, okay. This is the technique we use. This is using like the recipe from Paola Caselli in 1998, and this is you can use these deuterated molecules of the ion molecules to obtain these values, okay. So now here in this right plot, what I show you is the ionization rate as a function of the radius. We did some elliptical annular averaging, okay. Forget about the Brown scale where we don't have the spatial resolutions to do that, but this is the ionization fraction as a function of radius. And you can see clearly the ionization rate increases toward the center, okay. So what we try to do, and that was something done by Marco Padovani, is to predict which is the ionization rate if you have flares for the typical T Tauri star. Okay, take into account that you have the extinction. Okay, when the rays go from the star toward the envelope, you will have extinction. Okay, so we will decrease the ionization rate as a function of radius, and the values we obtain for the typical T Tauri star is order of magnitude lower. So this ionization rate is produced locally because you see the increase toward the center, but cannot be produced by X-rays, even less by UV photons. UV photons will be only important in the surface of the outflow cavity. So that means the protostars, or during this accretion burst, you probably create these low energy cosmic rays. So the protostars are probably factories of low energy cosmic rays, and that's what we produce this kind of stuff. Okay, so in this case, at least in this case, we know ionization fraction is high enough so the magnetic field is well coupled to the gas. In fact, if these absolute values are real, means this is a pure MHD, ideal MHD situation. And this probably explains why you have a so much smaller disk than the other regions. Maybe there has been like a period during 10,000, 100,000 years of a strong accretion burst that produces local cosmic rays. These ionize at high level the molecular gas. So you have a well-coupled magnetic field with the gas, and this allows to removing the angular momentum and not allowing this to grow strong enough.
Could it be reconnection near the center?
We don't, I mean, near the center, you're talking about like a few AUs. We don't have the angular solution. So any physical processes that is below 100 AU, we have no information. And the dust is going to be optically thick. So the millimeter wave length is going to be difficult to see. I mean, we could go to the BLA at longer wavelengths to see if there is non-thermal emission that could be related with.
No, what I mean is that magnetic reconnection could be the source for ionization there.
Okay, and the production of cosmic rays too?
Yeah.
Yeah, okay. Yeah, I mean, the physical process is not well. I mean, the problem is with this data, we cannot say which is the, yeah, so magnetic recognition, any physical process that can produce, or yeah, these high energy particles. Yeah. So that could be also in the jet, I don't know, during the creation phase, reconnection, I don't know. That's something, this is like a homework for the theoretical people to give us the answer. Which are the physical mechanisms that produce these local cosmic rays, okay? Okay, so now, so the answer is, yeah, at least in one source, and there are, I already know in other regions that has been already, not yet published, but we know from other data, this is not the only case. In Perseus, there are also other regions where you see this increase of ionization toward the position of younger stars. So this may be more, this is going to be very relevant, and it's telling us that, yeah, that polarization is going to give us the properties of the way to study magnetic fields, which apparently are relevant during the accretion phase and the star formation. So now let's move to data, specific now results. Now we could answer these two questions about different surveys we are doing. Let me first present, how much time do I have? 10 minutes, okay. So let me just go briefly to the BOPS, SB Field Orion Protostellar Survey. This is the PI is Ian Stephen in the US, but one of my PhD students is taking a role in the data reduction of that. And this is basically a survey in Orion. Orion is the closest molecular cloud that is forming massive stars. So it's a very good place to study the overall star formation properties in a very massive region, okay, and very dynamic regions. So what we did is around 400 parsecs away from us. So we used the HOPS. HOPS survey was a survey done with Herschel to study all the protostellar stars that are in the Orion. And we selected about 57 of them that has the signatures of being in the earliest stages, okay? And we observed them with ALMA. So here you have the Orion B and Orion A molecular cloud. And all these dots are the field of view we use to study the dust polarization in this protostellar cores to study the properties of magnetic fields. Okay, so with ALMA, we trace basically scales between 400 and 2000 AUs. Okay, so this will be the inner envelope. We don't get the information of the outer envelope. Okay, and we was observations where we combine continuum emission to get the dust polarization with CO line, the C322, which give us information of the outflows, which is also a good thing to have, and also some spectral lines like C17O. So here, the red and blue is the red shifted and blue shifted gas from the molecular outflow, okay, the lobes, okay. The gray scale is the dust continuum, okay. And the segments here, the blue segments, is the magnetic field. Once we flip 90 degrees the polarization angle, okay. So you have just 9 of them, we have 57, just to show you the diversity of molecular, of magnetic field configurations we observe in the same region. So you see kind of a spiral pattern, like this is a double a binary separated by like a 2000 AUs, and you see the magnetic field around each protostars has kind of this spiral pattern. So probably angular momentum is making the perturbation of the magnetic field having this kind of spiral pattern. In some cases, you see the magnetic field just following the outflow. Here you have this kind of strange shape too. And in some cases, you have magnetic fields aligned with the outflow, and in some cases perpendicular. So you have a diversity, and we have some overlaps too. It's not showing here. Okay. So what we did, the first thing to do is are the magnetic fields correlated with the direction of the outflow? And this is just to compare with previous results. Previous results at core scales, they show the magnetic field direction is not correlated. There is no correlation with outflow direction. This is a work by Tishu-san, who also was involved. This is in massive protostars. This is also another work in low mass cores by Cha Ho using Karma. So we use the same technique like by Shank et al. In 2014 to see if there is any correlation. Okay, just look at here. We see that there is no correlation. So the mean angle of the magnetic field compared with the outflow, there is no correlation at all. Okay. However, as you can see here, the polarization doesn't trace the full core. Okay, So you are always biased to the regions that are has a higher polarization fraction. Okay, and this is something we don't understand yet. Okay, so what we did is split the data in 3 different samples, and what we did is use C17O as a tracer of the kinematics in the core. C17O is optically thin, so 12CO traces outflows because optically thick at the cloud velocities. C17O is going to trace the kinematics of the core. Okay, so we can measure the velocity gradient in the plane of the skies of the line of sight velocity component. Okay, with that we saw that we can divide the sample in 3 regions. One where we see no velocity gradient around the protostars. Another where you see random orientation. There is no clear orientation with respect to the outflow. And then we see another type of sources. This is more or less 1/3, where the velocity gradient is clearly perpendicular to the outflow. Okay, and then we did a study to comparing the magnetic field with the outflow for these different type of sources. This is a case with no distinct velocity gradient. The velocity gradient is very, very small. And we use that, we see no correlation. And here we are using the magnetic field only around 1000 AU around the protostars to avoid that the polarization intensity anisotropy where we see affects the results. No polarization. And this is work in progress, so be cautious about results. In other cases where we see a random alignment, so the velocity gradient is not well correlated with the outflow. In this case, we see kind of a bipolar, bimodal, but not clearly either. In this case, it's perpendicular, but you have a strong velocity, like a angle. Okay. And then the third case where we see a clear velocity gradient that is perpendicular to the outflow. These are 2 sources where the velocity gradient you can see is very high. It's very clear and it's perpendicular to the outflow. In this case, when you see the statistics of the alignment of the magnetic field with respect to the outflow, we see that. In these cases, where you have a clear velocity gradient that is perpendicular to the outflow, we see that in these cases, most of the sources, the magnetic field is perpendicular to the outflow. So this is telling us that probably in these cases, the angular momentum is strong to make the magnetic field go from initially approximately toroidal to toroidal. So at the scales of few hundred AU, the magnetic field is toroidal. And that will be a representation of which may be the mechanisms. Maybe at large scales, the magnetic field is poloidal, but when you go close to the protostar at the scales of few hundred, because of angular momentum, the magnetic field just follows the velocity of the angular momentum and becomes toroidal. Okay, so this is work in progress. So we still have to refine the analysis, but yeah, I think the results are like that. And this may be in correlation with a study we did with SMA, where we measured the velocity gradient, quantitatively the velocity gradient, and we compare the misalignment of the outflow with the magnetic field for different types of sources. Of course, this subject selection was one with SMA, where you have less sensitivity, but we see a correlation basically of a strong velocity gradients. A low velocity gradients usually you see a good alignment. Where you have a strong velocity gradients, you see usually the magnetic field is perpendicular. In addition, you have more fragmentation. Okay. And now I think I don't have much time, right? Okay, 5 minutes. Okay. So now I wanted just to show individual sources. We are doing this kind of work also with massive star forming regions. So regions are going to form O or B stars. So they have, the core has usually masses of at least few tens up to few hundred solar masses. And we wanted to study the properties of magnetic fields. So let me show you only 2 cases, okay? And let me skip all of them, the rest of them. So let me show Orion, which is a very interesting source, and then G31. So let's just move to Orion. No, G31 first. So G31 with SMA was one of the sources we first observed with SMA, and we found a magnetic field that is in a polarization pattern in angles that is in agreement with an hourglass. Okay, and we know there is a significant velocity gradient along the midplane. There is no outflow in this case. we found evidence that the magnetic field maybe is producing magnetic braking by measuring the rotation of the lines, the velocity rotation. So we wanted to see if this is confirmed with ALMA. You see now the SMA, and let's see how it looks like this with ALMA. You see the difference, right? Instead of few independent points, now you have hundreds of independent points, okay? And you see this kind of Barcelona soccer team color, blue and red, okay? It's not because I'm from Barcelona soccer team. It's just here we are showing observations with some model by fitting the data, assuming an hourglass from the Daniele Galli and Marco Pademani group, where they assume an hourglass shape with different, you can play with mass to flux ratio. And in addition, they put like a dog kind of a component, a toroidal component, which will be the force ratio between the poloidal and toroidal component to try to fit the data. And they do the proper radiative transfer to create synthetic vectors in the plane of the sky. So we can compare with ALMA data and also filter out with the ALMA pattern. And we can get a very good, despite of being a massive region, a very good fit, where this will be the best fit of the hourglass of the magnetic field. So you can see this hourglass is slightly twisted because of angular momentum, okay? And these are the scales, okay? In this case, the magnetic field we can fit constraint is around 10 milligauss, and it's slightly supercritical, which is kind of surprising because this is forming like a massive stars, and 10% of the strength of the magnetic field is in the poloidal component, okay? So it was a good fit. And then let's talk about just my five final slides on Orion KL. Orion KL is known of is a very well-known, is the massive star-forming regions, the closest one, and is known by the work done by Luis Felipe Rodriguez, where they found several years ago that when you see the radio emission of the stars and you measure them with time, it turned out that there's the most massive stars in the Orion KL, they are moving apart. And when you extrapolate the tracks toward the past, they are coming from the same origin. Okay, so there is evidence that about 500 years ago, there was like a three-body or more than three-body interaction of massive stars. Okay, so these have now this right away, and this has created an enormous explosion that is very well seen in the optical, in the near infrared, and also with ALMA in CO emission. Okay, and now more recent work, they have found other runaway stars that are product of this kind of N-body interaction, okay? And you see this Orion in the near infrared, you see these fingers clearly. These are this product of explosion. It was a huge explosion with a total energy involved of 10 to the 47, which is a lot, and you also see in the CO. So what we wanted to see, which is the magnetic field properties in this region where you have this explosion 500 years ago. So this is the ALMA. We did a mosaicing. So we are sampling up the order of 0.1 parsecs. This is the Orion filament. Here is where you have the explosion, the origin of the explosion. These are the hot cores around the explosion, where the properties of the hot cores are very different from other hot core regions. And this is because probably of the explosion. And when we see the magnetic field, when you go away from the origin of the explosion, you see the magnetic field is perpendicular to the filaments. And this is what you see at larger scales. So this is in agreement with the larger scales. But however, when you go to the inner part, what we see is a magnetic field that in some regions are basically radial, and with an origin center of the radial, which is more or less where the explosion was happening. So you see that the explosion has already affected the magnetic field, which has been basically blowing up everything. The gas, the magnetic field, and you have this kind of radial option. And here you can see this is the origin of the explosion. You can see here clearly the magnetic field going like in a radial direction. Okay, and from here we can derive which is the radio of the shock, the shock wave that's where the magnetic field is being involved. Okay, and let me just finish with that, and there will be the summary. And thank you very much. By the way, we have a review paper with Anael, Patrick Genevel, The Frontiers in Astronomy, with all this information and updated work on the what we know up to date of the magnetic fields in star-forming regions from the theoretical perspective and observational perspective. So you can download this paper.
Okay, so questions here in the room? No? Okay, one here.
Bueno, esto de en regiones de formación estelar, todo depende de la escala que estás viendo. El campo magnético cambia, la dirección cambia, la orientación y la intensidad y todo. Me llamó la atención lo de Orión, que la parte toroidal. ¿La escala es ya a nivel de disco o todavía es a nivel de core?
En Orion,
Sí.
que no es toroidal, es radial.
No, de estos flujos donde el campo magnético es paralelo o perpendicular al
Sí,
flujo.
sí. Okay,
El
así,
campo
in the box,
magnético
survey the box. So estábamos hablando de escalas del orden de, tenemos una resolución angular de 300 AUs, so no tenemos la resolución angular para ver a escalas de discos. So, serían escalas de la parte interna de la envoltura densa.
Entonces eso es un toroide con el campo magnético ya
Aparentemente
enrollado.
sí. I mean, ahora el estudiante Bo está reanalizando los datos porque teníamos inicialmente la posibilidad de que en el centro, porque tienes la emisión del polvo del disco y sabemos que si el disco tiene granos grandes, emitirán como self-scattering y producirán esa fake toroidal. Estamos quitando la parte del centro y dejando solo un anillo alrededor de la protoestrella y todavía los resultados siguen siendo iguales. La auto-scattering no es importante en este sentido. Sí, es toroidal a escalas de pocos centenares de AUs. Pero cuando miras a gran escala, el campo magnético entonces ya es diferente. Pero queríamos ver, porque el outflow, el flujo molecular, en principio se eyecta a escalas de pocas AUs o pocas decenas de AUs. Si quieres estudiar el campo, la correlación tienes que hacerlo a escalas que no sean muy alejadas. Pues entonces quizás la turbulencia o la fragmentación tienen más importancia en la morfología del campo magnético.
¿Qué tiene especial esa fuente comparada con las otras que el campo magnético es más alineado con el flujo?
Porque vemos simplemente porque vemos que la gradiente de velocidad es muy claro de allá y es perpendicular. Entonces quizás es que el momento angular en esas regiones que tienes una clara gradiente de velocidad es más importante y tanto desde un punto de vista energético el momento angular es suficiente para deformar el campo magnético en esa forma toroidal. Entonces lo que estamos haciendo ahora es intentar medir cuantitativamente cuál es el valor de la gradiente de velocidad, porque esos datos los tenemos, y ver si efectivamente ese es el caso.
¿Alguien más tiene una pregunta en Zoom? Creo que no hay preguntas en Zoom. Bueno, pues si no hay más preguntas, ¿tú tienes otra, Salvador?
Adelante, Salvador.
Sobre los discos.
Sí.
Ahí la dispersión afecta completamente para poder obtener la dirección del campo magnético. Pero en la parte externa tienes menos densidad de los discos, estoy pensando. Ahí en principio sí deberías de poder distinguir una dirección distinta del campo magnético a lo que ocurre en la parte central, que es la parte más densa y los granos de polvo son más grandes. ¿Eso se observa?
Bueno, es una cosa que se está haciendo, o sea, la transición entre la parte en la cual estás dominada por autoscattering de la parte dominada por granos que están polarizados porque están alineados con el campo magnético. Eso es muy interesante. El problema es que, por ejemplo, el autoscattering, esperas que el patrón sea completamente radial, pero si hay efectos de opacidad, en la parte externa esperarás un patrón que es básicamente azimutal, o sea, en forma de elipse. Entonces, ¿cómo comparas? Entonces es difícil de distinguir si eso es una componente del campo magnético, entonces sería poloidal. Entonces es difícil porque yo creo que la solución es buscar diferentes frecuencias con ALMA, porque el autoscattering lo que sí que sabemos es que es altamente dependiente con la frecuencia. Solo aparece cuando el tamaño de los granos de polvo máximos es un factor de la longitud de onda. Entonces aparece la polarización en un rango pequeño. Pero el problema es que hay que intentar convencer al TAC de ALMA que no solo con una banda, tenemos que hacer varias, siempre es muy difícil. Y luego lo que ves es que cuando cambias de banda, pasas de banda 6 a banda 3, el patrón no tiene nada que ver y no hay manera de explicarlo. Entonces te dicen, bueno, si es tan complejo y no sabes explicarlo, ¿para qué quieres otra banda, no? Convencer al TAC es muy difícil.
La última. Última. Coger una.
Sí, dime.
Sobre esto, la idea antigua que se tenía. Bueno, no, mejor esta otra. Lo que se mide es la fracción de polarización y la dirección del campo magnético. Pero me parece, tal vez me lo perdí. No se puede medir la intensidad del campo magnético con este tipo de observaciones, ¿verdad?
Tienes que hacerlo de manera indirecta. Directamente no. Tú lo que tienes simplemente es la proyección de la polarización del campo en el plano cielo. Y a partir de las perturbaciones del campo magnético, por ejemplo, utilizando modelos sencillos como de reloj de arena con una componente toroidal, que es lo que hacemos con Marco Padevano y Daniele Galli, pues entonces podemos restringir cuál es el campo magnético. O si no, a partir de la dispersión también puedes medir, suponiendo por que la dispersión está relacionada con la intensidad del campo magnético o con el cociente entre el campo magnético uniforme del turbulente, puedes sacar el campo magnético. Pero siempre son medidas indirectas, no directas.
O sea, la manera más directa de hacerlo es usando máseres, por ejemplo.
Sí, pero los másteres, sí, claro. O efectos Riemann en líneas como CN, pero actualmente ALMA está muy limitado.
Sí, esa era la pregunta. O sea, ¿no hay en la región milimétrica máseres o líneas que permitan hacer esto? Porque, por ejemplo, se detecta máser de agua en la región milimétrica, pero
sí.
creo que no es suficientemente intenso, ¿sí?
No lo sé, yo sé que se está intentando también en másteres de metanol, aquellos que están siendo, porque de másteres tienes los que tienen, los másteres los generas por colisión o por radiación. Los de colisión, el problema es que el campo magnético, estás midiendo el campo magnético en una región que está chocada. Entonces, si quieres inferir el campo magnético en la región no perturbada, tienes que hacer ciertas suposiciones de qué tipo de choque tienes. En cambio, los máseres de metanol que se excitan por radiación, esos te darían directamente el campo magnético de la región densa que estás trazando. Pero yo sé que Wouter Bleming está trabajando en eso, pero no estoy muy al día. Pepe, también tienes...
Otra pregunta aquí.
Sí, ¿se puede usar self-scattering para ver cuál es la distribución de tamaños de granos de polvo? O sea, censando en diferentes frecuencias, ver si eso te permite conocer la distribución.
Si tienes la suficiente resolución angular y en frecuencia, si tienes, por ejemplo, sabemos que ahora que esos discos protoplanetarios tienen anillos, ¿no? En regiones que son mucho más brillantes en el milimétrico y regiones que son mucho menos brillantes, y podría ser que hay una cierta... los discos tienen por anillos diferentes tipos de granos. Yo sé que hay grupos que están trabajando en eso.
O la distribución de los granos
de
tamaño.
Bueno,
Dependen de la
bueno, es una discusión porque lo que se hace normalmente es mRN, ¿no? Tipo de granos de polvo, pero yo con Vicent que he colaborado para estudiar la polarización en el régimen de Mie, allá él es muy escéptico de que esos distribución de granos de polvo que tú mides en el medio interestelar se apliquen, precisamente porque hay crecimiento de granos de polvo. Entonces, él utiliza modelos no sé, de diferentes perfiles, pero ajustar cuál es el más es muy difícil, por puro scattering. No sé, pero bueno, sí.
Bueno, pues si no hay más preguntas, le damos las gracias a Josep Miquel.
Sí.
Muchísimas gracias por el coloquio y nos vemos en la siguiente. Hasta luego.
Gracias. Okay.